Alright, let's jump into chapter 2, motion in a straight line. We're going to be talking about motion in 3 dimensions, mainly 2 dimensions actually, but the third dimension is really just adding the same type of motion in the z-coordinate. To look at the motion, we need to define some things like position, displacement, and average velocity, and then we'll start displacing things like instantaneous velocity and acceleration, and we'll learn how to work with those graphs and stuff in this chapter. I'll also derive some of the formulas that you have definitely used in physics in high school, but they probably never told you where they came from. So when we study motion, we're going to start out just looking in one direction. There's a reason for this. Like I said, the motion in the other directions just follow the same formulas. We just simplify it down to one dimension first, and let's basically look at motion on like a number line. This physics course is primarily classical mechanics, so we're describing motion of an object, and for now we're going to ignore the reason why there is motion. So we're ignoring, I can't spell, ignoring forces, or the things that cause the motion or the acceleration. We will learn more about that, trust me. We're going to learn all about forces and how they cause the acceleration. But first we're going to learn what's called kinematics. That is the equations that describe the motion. We're going to start in one dimension, and we're going to call that a straight line. When things move, we can categorize it into 3 types of motion, typically. One would be the translational motion, which is mainly what we're going to be studying at first. Then we'll introduce rotations, and then we'll look at vibrations or oscillations. So right now we're just looking at a point mass that has some velocity or some acceleration, and we're gonna not talk about vectors quite yet, but we will heavily in chapter 3, because just about everything in physics is a vector. Things like energy are not, time is not. I'll go over which are and which aren't, but you should have a good idea of that. I tutor a lot of high school physics. I know what you've learned. But for right now, we're just looking at something as a particle that does not rotate, it only translates. Okay, so let's start out with a couple definitions. What is position? Position literally just describes a point in space, a location of a point in space. From a reference point. That's very important. So if I said something was 2 feet away, let's go into meters. Let's say something's 2 meters away from me. That means I am that reference point. Let's make a number line. 1 meter, 2 meter. That object is 2 meters away from me. We are what we're calling 0. And if we were given a negative 2 meters, that would mean that we would be over here on the negative 2 side. So we will be dealing with negative positions, negative displacements, and such. So position just, right, if you had an XY coordinate system and you had some XY coordinate for some point, we'll get into this, but a vector describes the position of that point from some other position, and it's usually what we'll reference the origin, or we can make anything a reference point actually. Whatever ends up being helpful in solving our problem. I'll teach you a lot of those tips and tricks, especially when we get into energy methods. So we have position. If this was a vehicle, let's keep it on a number line where this is 0. And here's my sweet vehicle. If it moves out to some other point, then that vehicle is going to undergo a displacement. It has two positions now. Let's say this one started at 1 meter and this ends up over at 9 meters. And it traveled in this direction. We define displacement as the change in position. So in this case, the change in x. And whenever you see something like the change in x, change in y, it's always a x final minus x initial. The final minus the initial. Okay, and what do we get? If we put those numbers in, I get 9 meters minus 1 meter. That thing traveled 8 meters, which I bet you could have guessed, right? But we need to know these terms. That is its displacement. That's not its position. They are different. We need to know the difference when we read the problems. We need to know how to report our answer. Something interesting. What if someone, let's say, walks over this way, maybe a kilometer, and walks back this way, I don't know, another 2 kilometers or so, and then walks back to where they started. Their position would be 0 because they went back to the origin. And their displacement would end up being 0 because they ended up back at the origin, because x final minus x initial ends up equaling 0. The distance traveled, though, we would have to add up the distance here to the distance back to this distance to that distance back. So make sure you understand what the problem is asking for. Okay, so if we have something's position at 2 points, let's say we've got someone running and they're over here at some other time. Let's call this x1 and this x2, and this would be x is equal to 0. They are at x1 at t is equal to time 1, and they're at x2 at t is equal to t2. So we get a displacement equal to x final minus x initial, which is x2 minus x1 in this case. And we also get a change in time, or a delta t. That would be t2 minus t1. If we take the ratio of this to this, x final minus x1 over delta t, we get the average velocity. Okay. And this is a big one. It's important because what if we had a graph, and this is something's position versus time, and maybe it looks like this. If I know a position here at x1 comma t1 and some other position here at x2 comma t2, I can take a straight line between those, and this is our average velocity. Alright, and in a little bit we'll learn that if we shrink down that time interval, we're going to get to the instantaneous velocity, or the limit definition. But for now, if they ask for the average velocity, there you go. You just need 2 points and the time difference between how long it takes to get from one point to the other. If it happened to have, let's say we're looking at some x3 at t3 and some x4 at t4, and it gave us a negative slope. That's a negative velocity, or negative average velocity. In this case, we had a positive velocity because it was going up, positive slope. Alright, if we shrink this time interval down, so I'm just going to look at this one part of the curve. If we're interested right here and we just keep shrinking the time interval down, we will end up getting a tangent to the line. That tangent is the most accurate representation of the instantaneous velocity. So V instantaneous. And we'll find out that it's typically a vector, but we're going to learn about that in chapter 3. And how do we get this definition? Well, if we're just looking in one direction, we'll call it the V sub x direction. We get it from calculus 1. The limit definition is that the time interval, this thing right here, just keeps getting smaller and smaller and smaller, or approaches 0. The limit as delta t approaches 0 of that change in position over time gives us the calculus definition dx dt. So if you have x as a function of time and you have some equation, it could be 3e to the t times cosine of t. Who knows? It could be anything, a polynomial. We could take the derivative and find the slope or the instantaneous velocity at any time. So don't forget, the slope is equal to the instantaneous velocity. Alright, in the next video we will take this one step further.